Hi, welcome to Increasing and Decreasing Functions in the First Derivative Test. My name is Tuesday J. Johnson. I'm a lecturer at the University of Texas El Paso and an assistant professor at Doña Ana Community College. This is part 2 of a lecture on increasing and decreasing functions in the first derivative test. In one, it just would have been way too long, so I split it up into two. The first, we looked at polynomials, and now we're going to get into some more complicated functions using first derivative increasing and decreasing functions. This is for Calculus, Math 1411 at UTEP. Applications of differentiation comes to us from Chapter 3 of Larson's 11th edition Calculus. Section 3.3, Increasing and Decreasing Functions and the First Derivative Test. Part 2 is just more examples. So if you need the basics of it, make sure you go to Part 1 and see all the definitions and theorems and everything that we're using. Alright, so examples 1 and 2 were on the last lecture. Picking up here with example 3, it's another polynomial. We're going to find the critical numbers, find the open intervals on which the function is increasing or decreasing, and we're going to apply the first derivative test to identify all relative extrema. So, polynomial, f of x equals x to the fourth minus 32x plus 4. The first derivative is a 4x cubed minus 32. As the derivative is a polynomial, it's always defined. So a critical number will occur when the derivative is equal to 0. If 0 equals 4x cubed minus 32, I'm going to add 32 to both sides. I'm going to divide 32 by 4, and I'm going to get 8 is equal to x cubed. Therefore, my critical number is only x equals 2. My critical number divides my intervals, my number line into two intervals, everything to the left of 2 and everything to the right of 2. So I picked two test values. I used x equals 0 to the left, and I used x equals 3 to the right. Remember, you can use any values at all, and notice these aren't even to scale. I just labeled them somewhere. So in my derivative, my test points go in the derivative. F prime of 0 is negative 32, but I don't care that it's 32. I care that it's negative. F prime of 3, I'm going to put 3 cubed. 3 cubed is 27. 27 times 4, I don't know, but it's bigger than 32. So 4 times 3 cubed minus 32 is going to be a positive number. That's all I really care about, positive or negative. So we can see that the derivative being negative indicates decrease, derivative being positive indicates increase, and that's how I get my intervals. Increasing from 2 to infinity, decreasing from negative infinity to 2. Remember, these are intervals, always the smallest value on the left. The interval should always look like a number line, the same order. And with a critical number of 2, increasing and decreasing, I know that there's a local minimum at x equals 2. Right, from decreasing, going down to increasing, so I'm going to have a minimum. The minimum, we always find the value of the minimum from the original function. So the original function, I put in my 2, I get negative 44. Remember, the derivative tells us where to look, but the original function tells us what it is. So the derivative gave us x equals 2. The original function gives us the y value. Yeah, it's kind of weird looking, but here's the graph. We can see at 2, negative 44 is our minimum. The graph is decreasing and then increasing. Looking at the graph, I see 2 real zeros, which tells me this probably also has 2 complex zeros. That's a lesson for pre-calculus if you'd like to know more about that. So let's do something that's not a polynomial. Example 4 is f of x equals x minus 3 all to the 1/3 power. The derivative is 1/3 x minus 3 to the negative 2/3 times 1. Can't forget to multiply by the derivative of the inside. It's a good habit to get into, even if it's just 1. When I simplify, my 3 is in the denominator. My x minus 3 is to a negative power, so I take it to the denominator, make it positive. The denominator of my exponent is my index. The numerator sticks with the value, x minus 3 all squared, the cube root of that. 1 in my numerator. I know that this derivative is never equal to 0 because the numerator is never equal to 0. The derivative does not exist at x equals 3, but 3 is in the domain of the original function, so something's going on at x equals 3. Well, 3 is going to split our number line, so I pick a test value to the left and I pick a test value to the right. any test values. I could have used 4. I could have used 7.24136. I could have used negative 10,472. But come on, people, let's use easy values. So I put in 0 into the derivative. 0 minus 3 is negative 3. Negative 3 squared is 9. The cube root of 9 is positive, and multiply it by 3, it's still positive, and find the reciprocal, it's still positive. In fact, no matter what I put in this derivative, when I square inside the radical, that's going to make it positive. Assuming it's not 0, and we excluded the only 0. If that's positive, the cube root of a positive value is positive. 3 times a positive value is still positive, and positive divided by a positive is always going to be positive. Which tells me that this function is always increasing, never decreasing. So what's going on with that 3? That's weird. Well, critical number of x equals 3, increasing forever. Make sure I split that value because x equals 3 is a critical number. The derivative is not positive there. It's undefined there. And since the derivative never changes sign, there's no local minimum or maximum. Let's take a look at the graph. This is what's going on at x equals 3. This is what we call a vertical tangent line. A vertical tangent line, it's not a minimum, it's not a maximum, but there's something funky going on there. It's almost like the graph goes straight up before it continues on. But notice it's still increasing. Increasing. Vertical tangent line is why our derivative was undefined. Example 5. Getting to a rational function, f of x equals x over x plus 3. I'm going to use the quotient rule to find my derivative. So that's low d high minus high d low all over low squared. And we'll simplify it. And if you need to step through that and make sure I did it right, I encourage you to hit the pause button. That's one of the reasons why I record these videos. Pause is amazing. When I look at my derivative in simplified form, because the numerator is never 0, the derivative is never 0. The derivative is undefined where my denominator is 0, so the derivative is undefined and we have a critical number at x equals negative 3. So in my interval, which I was just too lazy to label here, negative 3, let's pretend that's a 3, is my critical number. I'm going to use a negative 4 and 0 as my test values. And I see that when I put negative 4 into the derivative, negative 4 plus 3 is negative 1. Negative 1 squared is 1. 3 over 1 is positive. When I put in 0, 3 over 3 squared, that's also positive. And I see that my function is increasing on the entire real number line, with the exception of 0. With the exception of negative 3. Exception of where the denominator of the derivative is 0. So it's increasing from negative 3, infinity to negative 3, and then again from negative 3 to infinity. We have to put that cut in there, though, because the negative 3, not in the domain of the function, not in the domain of the derivative either. Wrapping this all up, we know our critical number is x equals negative 3. We know the intervals of increase are negative infinity to negative 3 and negative 3 to infinity. It's never decreasing. The first derivative test says there's no sign change in derivative, so there are no extrema. Let's see what this looks like. Look at that. It's always increasing. We do have an asymptote here at x equals negative 3. So it is a very important part of the graph. Negative 3 is not in the domain of the function. Negative 3 is not in the domain of the derivative. No minimums, no maximums. This goes forever up, goes forever down. There we go. We have our answer. So let's make it harder. If f of x is x squared minus 3x minus 4 over x minus 2, I'm going to use the quotient rule again to find my derivative. So that's x minus 2 times 2x minus 3 minus, and then my numerator times 1, the derivative of my denominator, over the denominator squared. If I multiply my binomials here, and I use a process called FOIL, right, the acronym, first, outside, inside, last, 2x squared minus 3x minus 4x plus 6. And then I'll distribute my negative to everything that follows. So that's a negative x squared plus 3x plus 4. Denominator is still x minus 2 squared. When I combine my x squareds, I'll get 1x squared. I'll have negative 4x and 10 in my numerator over x minus 2 all squared. Yeah, sometimes finding the derivative takes up a whole page unto itself. Now, it just so happens that this numerator is never 0. It's never 0 because b squared minus 4ac is 16 minus 10. That's not right. That's 16 minus 40, if I do it correctly, which is negative, and negative under the radical leads us to imaginary roots or complex roots. So the derivative is never 0 for real numbers. The derivative is undefined when x equals 2, where the denominator is 0, and so that's our only critical number. Without using a number line now, I'm testing to the left of 2, so that's 0. When I put 0 in for x, I'll get 10 over whatever, the denominator's already squared. So 0 minus 2, sure, that's negative 2, but negative 2 squared is going to be positive. So 10 over a positive number is positive. To the right of 2, let's choose a value of 3. Notice in the denominator, because I cannot use a 2, my denominator is always going to be positive for any value I choose. So I just need to know the sign of the numerator. 3 squared is 9, minus 12 plus 10, that's 7, over a positive value is positive, and this function is also increasing from negative infinity to 2, union 2 to infinity. No sign change in the derivative, so no extrema. I know, pretty quick and easy. If you need to pause, go ahead. And yet again, we have a graph. For those of you that remember your pre-calculus, notice how the degree of the numerator is exactly 1 more than the degree of the denominator. So we have a slant or oblique asymptote running through here. Slant / oblique asymptote running through here, along with a vertical asymptote at x equals 2. Otherwise, the graph is always increasing. Trig, everybody's favorite. We had to get some trig in here. Let's let f of x be sine of x cosine of x plus 5 on the open interval from 0 to 2 pi. Finding my derivative, I'm going to use the product rule. So that is sine of x times minus sine of x, right? Sine of x times the derivative of cosine, plus cosine times the derivative of sine, and the derivative is cosine. And this is cosine squared, and here we have a minus sine squared, so I put in the proper order, cosine squared x minus sine squared x, just to make it easier to work with. The negative in front sometimes gets lost. Now, this is a trig function consisting solely of sines and cosines. Since sine is continuous and cosine is continuous, the squares of each are continuous, and also the difference of the two are continuous. Continuous everywhere, defined everywhere. My only critical numbers will be where the derivative is equal to 0. Uh-oh, I know, you're freaking out, right? We have to do some trig. You can handle this one. If 0 equals cosine squared x minus sine squared x, I'm going to add sine squared to both sides. And where are sine and cosine equal? They're equal at pi over 4. But because it's squared, we don't even have to worry about the positive or negative signs. It's actually pi over 4 in all 4 quadrants where these two are equal. So, I'm going to take some test points. And for some reason, they're not written down. My test point. Wow. Okay, first of all, my critical numbers are going to be at pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. It's an ugly pi, but we'll go with it. My test points will be pi over 6, pi over 2, use easy when we can, pi, 3 pi over 2, that's a 3 and that's a 2, and then we'll use 11 pi over 6 as a test point in our last interval. And I'm going to test them. Pi over 6, substitute in my derivative, I get 1/2. It's positive. That's what I care about. It's positive. So here, I am increasing. When I put in pi over 2 Pi over 2 gives me an output of -1, so I'm decreasing. Pi gives me an output of 1 in my derivative, so I'm increasing. 3 pi over 2 gives me an output of -1. And 11 pi over 6 gives me a positive 1/2. All I really care about, though, is the positive result. So I know I'm increasing from 0 to pi over 4. We're always splitting at our red marks here, our critical numbers. 0 to pi over 4 we're increasing, 3 pi over 4 to 5 pi over 4 we're increasing, and 7 pi over 4 to 2 pi we're increasing. Decreasing, pi over 4 to 3 pi over 4, and decreasing from 5 pi over 4 to 7 pi over 4. Yeah, it's challenging, but you can do it. So, apply the first derivative test. I know where I'm increasing, I know where I'm decreasing. At pi over 4, I switch from increase to decrease, so I have a maximum. Put pi over 4 in the original function, and we'll end up with 11/2 as our y value. At 3 pi over 4, I go from decreasing to increasing, so I have a minimum. At 5 pi over 4, a maximum, and at 7 pi over 4, a minimum. Now remember, these are intervals. Increasing and decreasing are intervals only involving x's, whereas maximums and minimums are points. This is x, y. So this is an interval of x values, whereas these are points in the form x comma y. Taking a look at the graph, I have a maximum of pi over 4, a minimum of 3 pi over 4, a maximum of 5 pi over 4, a minimum of 7 pi over 4. Everything looks exactly like we said it should. Alright, so let's do a word problem. Why not, right? Let's talk about coughing. Coughing forces the trachea, also known as the windpipe, to contract, which affects the velocity v of air passing through the trachea. The velocity of the air during coughing is given by v equals k times capital R minus little r quantity times r squared. And this is for 0 less than or equal to little r is less than big R, where k is a constant, r is the normal radius of the trachea, and little r is the radius during coughing. So I want to know what radius will produce a maximum air velocity, so whatever you're coughing will come out at the fastest possible speed. Well, we want to find r when the derivative is 0. All right, what radius will produce a maximum? Where is the maximum? So where tells us find r. When I take my derivative, remember k is a constant. So I'm really I'm leaving this k out in front, and then I'm taking the derivative of big R minus little r times r squared. Big R minus little r times 2r plus r squared times capital R, it's normal radius of the trachea, that's a constant. The little r is what's changing based on the cough radius. So the derivative of big R minus little r is -1. Multiply, combine like terms. I know that the derivative is 0 when this product is 0, so 2r minus little r times 2 big R minus 3 little r. Or that's when the radius is 0, or when the radius is 2r over r. Now I got to tell you something about a radius of 0. Remember, r is the radius of your throat, radius of the trachea during coughing. I do not recommend making your trachea close. I'm going to guess this is where the maximum airflow is, because a closed trachea flows no air. Let's see. Oh yeah, look, I didn't even bother with it. The critical number r equals 2r over 3 is a radius that is 2/3 the normal radius of your trachea in order to provide maximum velocity of a cough. If you could do that on purpose, you're a pretty amazing person. And I got to tell you, you're following along calculus, it's still pretty amazing. Thanks for listening.